Thank you. God, dim the lights, yeah. Right. This presentation tonight, I have to say that I cribbed it off of someone else, if you like. However, it's a good job that I looked through it, because the original presentation was 4 presentations long, 60 slides each presentation, and would have basically lasted the best part of 3 days. It was done as a lecture series. So I've cut it down as much as I possibly can, because, again, chatting with Don, he knows that this could go on for a long time. So I've tried to get the main points over, but there's a lot to it. I'm not just going to, I'm not going to talk particularly about amateur sats and things like that. This is satellite communications in general. So a lot of it will be about stuff on the military sites, stuff on the commercial sites, and things like that. So, but I hope you sort of get the gist of it all and enjoy what's going on. So let's see how we get on. Right. A satellite link consists of basically something very simple. A ground station link, which may consist of up converters, amplifiers, filters, and antennas, goes through the satellite, and there's things happening up there, and then it comes down here with an antenna, filter, low noise amplifier, down converters, and this comes in here with modems, because most of the stuff now is all digital. It is not, you don't use analog anymore. Even in voice, you don't use analog anymore. Even voice is all digitized. So that's it. That's basically it. That's satellite technology. Thank you very much. We'll see. Oh. Right. Now, there are a number of different types of satellites. We'll start off with the first one, which are geostationary satellites. Now, these are the ones that are way up there, nearly 36,000 kilometers away. And although they calls them stationary, geostationary, they're actually traveling at 11,000 miles an hour, which happens to be at 38 kilometers above, 38,000 kilometers, 36,000 kilometers above the surface, the same speed at which the Earth is going round. So, as the Earth is going round like that, the satellite is going round at the same time, and so it appears to be stationary. So, that's it. So one orbit takes 24 hours, and it's going at the same speed as the Earth. Now, the problem with satellites that are put there is that even if you have illuminate the whole of the Earth, you can't. You can illuminate it around the equator and all the way out to roughly plus or minus 77 degrees above and below the equator. But the poles, top at the bottom, are not illuminated at all. So it's no good trying to go up to the Arctic and think you're going to watch satellite TV. It's not going to be there. Now, other things are orbital locations are regulated by the International Telecommunication Union. We all know that one, ITU, and there's loads of regulations concerning it. Now, people say, how many satellites are up there? You know, there's 2 or 3, isn't there? Well, if you go from the horizon eastwards through to the horizon westwards, there is one satellite every 1.5 to 2 degrees as you go over that arc. So there's hundreds of them, literally hundreds. Some are all broadcasting on the same frequency. Some are on different frequencies, and so on and so forth. So Earth stations' antennas will illuminate multiples of satellites and things like that. And you can't do that if they're spaced too close, because even with a very big dish, with only a narrow beam on it, you can quite easily beam into your neighbour's satellite as well as your own. And this is a problem, because if you're trying to gain money from this, i.e. you're selling your satellite time to somebody, and you happen to be pointing in somebody else's satellite, i.e. crapping in their own backyard, they don't like it. And they get very annoyed and say, you're crapping in my backyard, and you've stopped me earning money, and I want compensation. So everybody is very careful into what it is they do. So all of the orbital slots are measured in degrees, going east from the Greenwich meridian at 0. Now, one of the other things, if you ever want to find out about what satellite's up there, there's a site called Celesttract on the internet, and you have to look up a thing called TLEs, known as two-line elements. They're just simply a coded word, and it tells you exactly what the satellite is, what it's doing, where it's going, and what it should be doing. Okay, so satellite antenna beam width is 17.3 degrees for all. That's if you've got one antenna on the satellite and it's looking at the Earth, it needs to be 17.3 degrees beam width, and then it'll cover all of the Earth east to west, but not north to south, as we've already discovered. Right. Advantages and disadvantages of geostationary synchronous satellites. So, no ground station tracking required. That's not strictly true, but basically speaking, yeah, you can point it up and there, and we ain't got to do anything. It'll stay there like that for the rest of the day. However, if you've got a big dish with a very narrow beam, even a geostationary satellite wobbles. The wobble is roughly inside a box, 140 kilometers square. Now, with your little sky dish, which is about 2 feet across, you've got a beam width of 3.5 degrees. So 140 kilometers out of 36,000 kilometers is a very small angle, and you can't see it, the difference as it wobbles. So to you can fix it, and there it's all done. If you've got a 13-meter dish with a beam width of 0.2 of a degree, it can see 140 kilometers wobble. So it does have to track it. Now, I did some work with nothing more than a 6-meter dish out in Saudi Arabia. And once it was all set up and the antenna had to track it, you could hear it going click, 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 all the time, as it was basically following the geostationary satellite up in the sky. Right, this is a thing which probably most of amateurs don't realise and know about, and this is a thing called Doppler shift. Now, because the satellite moves, it has a Doppler effect. That's, the ambulance siren going past you and things like that. Well, geostationary satellites don't appear to move, so it doesn't have a Doppler effect. But we'll come on to that later on when we look at other satellites. Disadvantages, as we've said, it's 36,000 kilometers away. That means there's a very tiny little signal, which we'll come into later on. Poor coverage above 77. And the biggest problem is the weather. Particularly as we go up in frequency, weather has quite a significant impact. I won't go over this too much, but as I said, the satellites, even the geostationary ones, they wobble. They wobble because the Earth, if you like, basically has a gravitational pull, so it's going to pull it this way and then pull it the other way. And there are all manner of other effects, which is why you get the wobbles. The problem is that in order to keep it where it is, you've got to have a thing called fuel, stuff known as hydrazine. that when it's sent up, you've got these great big canisters, a bit like, you know, Kaler gas canisters you get there. So you've got a couple of those. Now, they don't squirt out often like what people think they do, squirting out the side here and there to keep it on. They actually squirt into great big circular wheels, which act like gyros. And it is those that are keeping the thing steady. Right, won't bother too much more about that because there's so much more to get through. Right, going the wrong way. Non-geostationary ones. Now, there's loads of different types of these. So, first of all, there's the one we call medium Earth orbits. They're between 10 and 20,000 kilometers. And then there's a lot in this range called low Earth orbits, which are 150 to 500 kilometers. So if you've ever looked out in a starlit sky and you've seen odd white dots going over the thing, that's Mr. Musk and his little bunch of satellites. And they're up. I think Musk has got his at around 400 kilometers, somewhere like that. International Space Station is at 250 kilometers, if you want to know how high that one is. So it in its right is a low Earth orbit satellite. Now, the advantage of these are, first of all, because you've only got to get it up 250 kilometers or so, it's a darn sight cheaper than it is trying to get something up at 36,000 kilometers. So launch costs are cheaper. Low power, and shorter transmission delays. That can be a bit of a problem when you're running digitals. You don't want the, you know, it's like what you hear when you see the presenters on the television and they're not quite in sync with the presenters in the studio, and the other one's 10,000 miles away, and there's this gap, and you've got this dead silence. Whereas if you're talking through a low-cost satellite, which they do a lot now, there's virtually no delay at all. Disadvantages is the fact that just as you've got the satellite and it's coming over and everything's great, it's gone over there and it's disappeared on you. So you need lots of satellites so that you don't get the interruptions. So you need potentially large constellations. I think Mr. Musk is up at 720 at the moment. And I think he wants to go up to 1,028 and possibly more. Potential for 5,000 satellites is what he wants to get to. So the big problems you've got is between the LEO orbits at around 500 kilometers and the MEO orbit at 10,000 kilometers, you've got this thing known as the Van Allen belt. It's a weird piece of stuff up there in the sky. I'm not going to go into it. It takes too long. But that's where you've got those. You've got one at somewhere around about 2,000 or 3,000 kilometers, and then you've got another one up at about 15,000 kilometers. And they can cause all manner of problems. You know all about the Van Allen belts because sometimes radio signals that we do reflect off the Van Allen belts. And you probably weren't even aware of that. Right. One way of overcoming some of the problems, if you've got all of these different sorts of satellites, you can have them going around this way, this way, this way, and so on, is that you can get them to circle via the North and the South Pole, which is great because now we can send signals from the North and the South Pole, which we couldn't before with our geostationary satellites. So, and if you use a number of those, every customer is always in a footprint for some period of time, why you can see it. And obviously, the higher, the further and further out you go, the less the number of satellites you need. The only problem is, of course, the further and further away you go, then the more power you need to get your signal up there and back again. So there's always trade-offs here, there, and everywhere. The last sort are called Moynier. Very weird name. It was basically something that the Russians used a lot. And these... Moynier. Moynier. All right, comrade. They are... they're elliptical orbits. So the whole idea is that instead of it going round in a nice circle, it goes way out there and then comes back and then whizzes round the bottom again and then goes way out and whizzes. So that while it's in this bit going up and round there, is longer than it would have been if it was just going round and round. So that's the way they worked it, so that the bit round here comes round a lot quicker, and then you've got this lasting a lot longer. But they're not so easy to get them to do that because it's a weird thing. But that's the sort of last type. One thing that's come along of more recent times are called MEO satellites. And there's a company called O3b, which are using these, OneWeb. The only problem is that this is where you can see the coverage. And basically, if you've got a series of medium orbits around the equator here, which is great, but we don't get a look in. So, but the number of satellite companies are looking into that. You can see the fact that we don't get a look in, but if you look at the United States, it basically it covers most of that very nicely, thank you very much. So, of course, they're very keen on this sort of thing. So that's medium satellites. Right. What is in the satellite? Well, basically speaking, we call them bent pipes. They are a technical term, bent pipe, i.e. it's a pipe like that, so you squirt it up inside this way and then it squirts out at that end. But what's in there? We all know and work with, or have done, worked with repeaters. And it basically does exactly the same thing, except we have to be a little bit more constructive with it. So in comes the signal into the, if you like, the picking up antenna. So we've got that coming in, and the first thing we can do is we've got to amplify it, because this has come in at minus 190 to minus 230 dBm. It's tiny. This has probably got a gain of about 40. So that's not helping a lot, but of course it's helping a bit. So we need a bit of an amplification in here, trying to get that up to a decent level. We'll put it into a filter, just to clean up any rubbish that's come up as well. We then put it into a mixer, because this is coming up, say, if you're like your satellite TV that you're watching, this is coming up at 13 gigs. So we pass it through there, and then we put a local oscillator in, which basically is about 2 gigs, and it cuts the 13 gigs down to 11, which is the same as the repeater unit that you have, but it goes in at 145.5 and it comes out at 145.6, or the likes. So we have a local oscillator, changes the frequency, bandpass filter, again, to clear up all the rubbish, put it into a thing usually called a TWTA, Travelling Wave Tube Amplifier, which is basically a microwave valve. And the reason why they tend to use those is that they're voltage amplifiers. They don't use a lot of current, and they can last forever and ever, but they do get soft over time, like any valve. So this kicks out about 100 watts, maybe 200 watts if you're lucky, 100 to 200 watts, this amplifier here, and then puts it back into another antenna, which could be all manner of different antennas. Now, this is basically capturing everything, but this one is doing different things, because this antenna here has probably got a number of sort of branches off, depending on what you want to do. One antenna shines down over there, another one shines down over there, another one shines down over there. Now, some of the antennas, if you like, are very narrow beam. So, for example, if you think of the Astra satellite, it's got a beam that shines down literally, and the maximum part of the beam covers the UK up to just about the Scottish borders. Although you can get it a little bit further south as well. But then also there's another antenna that sort of shines over there, and that covers loads of Europe as well. And then there's another one that covers even more. So that's the way these things work. And in when we're talking about probably things like military and other satellites, these beams actually can be quite small, so that you can, say, put a beam down on Minnesota and then put another one down in Ohio and then put another one down in Florida, so you can squirt them all over different regions, depending on what you want to do with it. Sorry, some of those are taken from the military side. So these are military frequencies. Not that one, but this one is. Not that it's not a secret. Don't worry. Okay. Now, the satellite is, if you like, built up into what's called transponders. That is to say, although you've got a bandwidth that the satellite works over, that's then segmented up into different things. So that TWTA that we talked about a moment ago, you will have one for each of these different bandwidths. And there could be anything up to 6 or 7 up there. And again, they could be attached in different ways to different antennas. So the transponders are characterized by center frequency, their bandwidth, their power, the amount of power that they're producing out, not only from the amplifier, but the antenna that's attached to them. Obviously, because the EIRP, that's the overall power, is a function of the amplifier and the antenna that's attached to. And so different transponders will have different powers. And, of course, the companies that run the satellite itself decide where you put things. So they'll probably have one transponder. Let's call it this one here, because that's a nice narrow one there. And they'll have, let's say, probably 1,000 telecom channels in there, because they're all very narrow. And so this thing may be, maybe about 300 or 400 megs wide, but they've got 1,000 telephone channels in it. Whereas this one here is running television, and it's got about 8 or 10 or 12 different television channels in there, again, depending on what you want, if you 4K television or just ordinary or whatever. And then this one could be used for something else again, and you allocate accordingly. So those are the different things. There's also the thing polarization. Now, you sort of understand polarization. So you can either transmit in the vertical plane, you can transmit in the horizontal plane, and you can also basically add the two together and transmit circular polarized. Now, most of the television channels that you watch have got both vertical planes and horizontal planes. And that means to say that you can actually sort of, if you like, you can get two channels. You get that one and that one all at the same time. So you haven't got to worry just about that or that. You can have both. So that one transmits one lot, one that transmits another lot. The military tend to use circular polarization. Now, the reasoning behind is this. When we talk about vertical polarization, there it is like that. That's great, isn't it? Fine. Now, if you're on the ground and you're transmitting to me and I'm vertically polarized like that, that's great. So you transmit to me a vertical polarized signal. Good. Right. Now, I'm going to move my satellite around the world. And the problem is that as I move it around the world, my vertical suddenly doesn't become vertical anymore. It starts to keel over. Now, if you look at your satellite dish feed, it's not vertical, it's tilted over. Why? Because the satellite you're looking at is at 29.2 degrees east. So it's not on the Greenwich meridian and will be like this. It's moved round the world and it's like this. So that once if you got all the way over there to 90 degrees, it would be horizontally polarized. That may be a bit of getting through to your head, but that's the way it works. So they're both doing that. So your vertical one's become horizontal, and your horizontal one has now become vertical. But that's fine. Wherever you are, you just tilt your feed until you get the right angle and everything's fine. So it's still doing that. So you still got this vertical one and this horizontal one, albeit that they're all skewed round by so many degrees. That's great because when you're at home and you've got a dish on the wall, it doesn't matter. It's always going to be like that because the satellite is always in the same place. If you're a Royal Naval ship and you're working a satellite that's, let's say, on the Greenwich meridian, great. And then you go 2,000 miles away across the Atlantic, your antennas have got to keep doing this all the time. So they don't want that. So they use circular polarization. So their thing is doing this. Their waves are doing this all the time, circularly polarized. So it doesn't matter where they are in the Earth, it's always going to look like this. So they never have to move their feeds in the same way as a person would have to do if you were on normal land. Now, for example, if you're into trying to watch football or something via one of the European satellites, that's at 19.8. So your feed will have to move very slightly from where it is for the Sky Astra for the at 28 to the European version at 19. So polarization suddenly becomes quite important. I'll move on. Right. Earth stations. So we've done what's up in there in the satellite, and to get up to the satellite itself, this is what an Earth station looks like. The first thing you start off with is a whole bank of modems here. I've only shown 4, but this could be goodness knows how many. These are all digital modems, and their output is all put into a nice combiner. And then, because we put it into a combiner, we've got to sort it out, make sure it's all clean and tidy. And then we turn it into an up converter, because this is probably working This is working at about 1 gigahertz. So digital signals go in here, and 1 gigahertz-ish comes out here. They're roughly 500 megs or so wide, each one of these. So to work it on into your satellite, which is, if you like, your television signals, this has got to come up to 13 gigs up here. So we need to, what we call, up-convert it. And then into our high-power amplifiers. This time, because we're on the ground stations, we have an infinite power supply. Oh, that was one thing I meant to mention about the satellite. You have to remember that the satellite does not have infinite power. Therefore, you can't use bigger and bigger amplifiers because you don't have the power to drive them. On the ground station here, these are kilowatts. Much, much bigger fellas. And we then filter it all, and we put it into this thing. This is called an OMT. It's called a transducer, an ortho-mode transducer, which basically is the thing that you use to mix your incoming signal with your outgoing signal so that you can use the same feed in your antenna. So that's fed into this, and that then transmits out to the satellite, and then your incoming receive signal goes back, if you like, by a similar method. You have a filter, a low noise amplifier. Sorry, this is slightly wrong there, but it's meant to get it. And then down converted, split out, and then fed into the various modems. So that's very simplistic. A couple of things that we have to be aware of, though. One of the things is, although I said that the amplifiers here, and there's two, not because we need two amplifiers, in fact, we move more than that, but these are called redundancy. So if this one goes wrong, this switch switches, and this one comes into play, and everything carries on. You don't notice the join, if you see what I mean. And the same is true for your up converter. So we always have redundant systems when we're in the professional world. it'd be like if you had your FT100D here and another FT somewhere, or a trio something over here, and as soon as this one went wrong, this one came straight into play, and you carried on. And the same thing is true on the downside link, that you've got the LNAs are in a redundancy mode, so if one drops out, then we go over to the next, and the down converters in the same way. Now, there's a couple of other things that are essential. As we've said, although the satellite may be geostationary, and it's not, it moves. And you've got to be able to track it. Now, one of the things that all satellites have is a thing called a beacon. And I'll go on a bit more about beacons. But basically, it's a tiny little signal that's stuffed in the middle of all the other ones. And each satellite has a unique beacon frequency, or pretty much unique. So that when you squirt your antenna at the sky and looking for the satellite, and you think, how do I know where it is? You look for the beacon. Once the system sees the beacon, it can then home in on it, peak the beacon signal, and it knows that it's in the right place. So we've got a beacon receiver that comes out of the receive side that is there just to pick up the beacon signal. The output of that is usually, if you like, a couple of DC voltages, which then basically go into an antenna control unit, which then goes into the various ways in which the antenna is controlled with encoders and things like that, and keeps this thing nicely on track. So that's how you get with an earth station. Now, even though this thing here can kick out, let's say, a kilowatt, 1, 2 kilowatts, great big. The actual size of the signal per, if you like, per frequency that it kicks out, or per channel that it's going to use to kick it out, maybe only about 5 watts. And you don't need 1,000 watts to get it to the satellite. You only need a few watts. This thing is doing all the work. This thing's got a gain of 50, 54, 55, anything up to 60. And that even though you may need, and this is why you learn about dBs and not about watts, because the wattage that's coming out of there is like 30 billion watts. Now get your head around that. You can't. But if you said that the wattage coming out of here was 64 dBs, you think, okay, fine. Understand that. 64? Yeah, it's a number I can deal with. It's in my head, 64. And then you do all the others and all the other numbers and the calculations. And yeah, it doesn't look quite so bad. But if you said this is kicking out billions of watts, you'd think, ah. Now, so this thing can produce 1,000 watts, but one of the things it does, or we have to do, which, if you like, as amateurs, we hardly ever do, and that is called back it off. So 1,000 watts go out. However, we back the amplifier off 3 dBs, so we've lost 500 watts straight away. We back it off. We've now got 500 watts coming out of one of these, and we probably might even back it off even more than that. Why do we back it off? What does that do? It turns your signal, making sure that it only works in the linear section. If you run it at full saturated power, you could be up above what we call P1, and you're no longer linear, and therefore you don't know what crap you're creating. Back it off 3 or 4 dBs, and then you know you're in the linear region. So it's automatically a thing you do. Back it off 3 dBs straight away. So this is now running linear. But the other thing is, you're going to have, unlike an amateur who transmits one signal, this thing is going to be transmitting, as I've already said, probably 1,000 signals from a telecom system, plus about 20 TV channels as different frequencies. So you've got loads and loads of frequencies. Now, this then becomes important, and why you actually are only transmitting, let's say, 5 watts per television channel. One of the things you have to remember when you're doing things like radio is that if you transmit frequency 1, there it is, that's lovely. No problem at all. Nice, crisp signal. That's what amateurs do. Right. But now we're going to add another signal here within our frequency band. So we got frequency 1 and we got frequency 2. And the first thing that happens is those two are going to do something. They're going to add and they're going to subtract. So you've now got a frequency 3 and a frequency 4 and probably a frequency 5. Now they're all going out of here, and some you might be able to clear up with the filtering, others you might not. They might still be in band. If we were broadcasting 500 watts here and 500 watts there, the thing that comes up here in the middle is probably going to be about 20 or 30 watts. And when I said if we crap in somebody else's backyard, they won't like it, that's one of the things that happens. So you keep the power here as low as you possibly can just enough to make sure that you actually can make what we call the link from A through the satellite down to B. So that has to be kept as low as possible, because as soon as you start putting the power up, this thing in the middle starts creeping up, and eventually it'll reach a point where you crap in somebody's backyard and suddenly find yourself fined by somebody for a lot of money because he can't make his transmission. So, yes, you don't broadcast 1,000 watts. You're only broadcasting per frequency barely 2, 3, maybe 5 watts maximum. That's all it is, and that's all it takes. I think I was running a 4 megahertz signal out of a 6-meter dish from Riyadh, and we were using half a watt. So that gives you an idea of, Right, so signals. Satellite signals cover wide areas. There's many users. Site has no idea what the other site is doing, but everybody has to coexist and work by the rules, which we've already said. You can't crap on somebody else's backyard, so that's important. There's our signal path, as we've already mentioned. So we've got an uplink, we've got our bent pipe, and it comes back down on the other side. Data in and then data out. And somebody has to actually try and work that out. That was my job. That's what I have to do. And that's why I tell you about using dBs, because everything, if you like, from this point onwards is worked in dBs. You can't do it any other way. Even though these things may have watts available to them, you don't do it in watts. You've got this coming out of here probably at about minus 40 dBm. That goes out here to the power amplifier. That's coming out, let's say, at 3 watts, so that's 2 or 3 dBm. Antenna has then got a gain of 50, so you've got 52. And then that thing, path, that's your big problem. The big problem is you're going to lose all that energy getting up to the satellite. Now, a KU band, 13 gigs, as it's called, that's going to be around about 210. So you've started out here, you've got 50 dBW or 80 dBm. If you want to know the difference between W's and M's, you've got to add 30. And then you lose 210. So what you've got coming in here is about minus 150. So this has now got to get rid of all of that and amplify as much as you possibly can. This one will again have an output of about 100 watts, backed off. So it's only really got about 50 watts. And then the path back down, you lose another 210. So you need another antenna down here. However, this link, the one on the way up, because you have got access to, if you like, all the world's resources down there, that's the strongest link. This bit coming down here is your weakest link, because it's likely to be smaller and so on and so forth, and it's got to deal with all the crap that you've created going up and around there. So, transmitted power, we've already looked at this. EIRP, effective isotropic radiated power. The word isotropic comes in here. So when you talk about EIRP, what the hell does that mean? Oh, you say, oh, well, that's the power you radiated. But did you know that I in there means isotropic? That is to say, the isotropic is a sphere. Right. So it's the point isotropic radiated power emitted from a point source. So it's a point source, and out it comes. And then you can do some really, if you really want to look into it, there's some flashy bits of mathematics down there, but I won't bother to go into it. But if you want to sit there or look at this after all, you can then look at the way in which the maths works as well. Right, so a directional antenna emits radiation in a solid angle. So now, your nice beamy thing is going to start from this isotropic point and slowly do this to the d squared law, or the 1 over d squared law. So every time you move twice the distance, you lose 6 dBs. Okay? That's the way it works. We're fortunate that in the space industry, there's nothing to get in the way, and therefore it does work to the d squared law. Down on, if you work in 2 meters and 70 sems, it don't work necessarily to the the d squared law, because you have other things that come into play. You've got bounces off of walls and hills and trees and cars and everything else. So that doesn't quite work. I won't go too much into of all the mathematics, but basically that's the way in which thing radiates. Now, so the EIRP is the transmitter output plus the antenna gain, which is useful. And you do that yourself, so that doesn't take much. But it has to include not just the antenna gain, the antenna efficiency. Now, again, for most of you that work with HF and etc., you don't worry about the antenna efficiency. As far as you're concerned, you put RF into it and it radiates it. The efficiency of most antennas should be a good 99%. An antenna like this one has an efficiency of about 60%. 65% is good. And when we use things called phased arrays, we might push it up to about 70%. But more often than not, we're somewhere working between 50 and 65% efficiency. So although we start off with an antenna gain here of, say, 50, that's how you calculate it from the size of the dish, etc. What we've actually got is slightly less than that because it's only 65% efficient. So we've got the antenna efficiency, you've got the transmitter output power, you've got also here, because we're working in frequencies way up the band now, anywhere from 3 gigs through to 40, 50 gigs. We've got coupling losses, waveguide losses, and all of the other things. So once the ERP is known, no additional information about the transmitter is required. So we can then use those numbers to do the calculations that we want to see whether or not the whole thing is going to work. Path loss. Again, here's this time our isotropic radiator. And as we've said, it's when we transmit, we don't just, you're transmitting through space and you start losing power. This is the thing about, everybody complaining about this 5G thingy down by the school, that really, if they understood the 1 over d squared law and the way in which you get path losses, etc., you'd realise that actually by the time you're 20 feet away from the antenna, and that would be actually at the height of the antenna, you've got next to nothing. Although that may push out 10 watts, by the time you're about 50 feet.
Read the Guardian, you see, so they know it's bad.
And they know it's bad. What is strange is the fact that they seem to be very, they're worried about 5G being mysterious. But as Don and I know, all they've done is they've gone from 16 QAM up to 64 QAM. which is a modulation thing. It is the way in which you modulate the signal. It's got nothing whatsoever to do with anything else in the signal. Right, so path loss is basically a dispersion of the transmitted signal. As it goes away, the signal gets wider and wider and wider and bigger and bigger and bigger, and you start to lose your power. Whereas you're only taking just a little bit here in the middle from it, so it gets quite small. Don't worry about that if you don't want to, but get your calculators out if you do. Path loss is related to the number of wavelengths. That's the main thing, the number of wavelengths. So the path loss at 3 gigs, right, where the wavelength is this long, is totally different from the path loss at 13 gigs, where it's that much. And if you go up to 30 gigs, which is where I often work with, it's about that much, 3 millimeters. Right, but it's still proportional to d over lambda. That's the main thing. It's still got this 1 over d squared law going. It's one of those things that you tell everybody about the Voyager satellite and the fact that they're picking up the Voyager satellite now, and it is, whatever it is, 30 billion miles away from Earth.
Beyond Pluto, isn't it?
And yet, how far has it got to go? And I mean, it's been up there since 1974, so it's 30 years that it's been going. How far has it got to go to lose 6 dBs if it's 30 billion miles away? And the answer is another 30 billion miles, which means that to lose just 6 dBs now, it's got to literally go another 30, 40, 50 years. The trouble is, it's not that, it's the, if you like, it's the power source that it's using is running out. So unfortunately, sometime it's going to die simply because there is no power. However, they managed to turn it a few months ago. So they're still in communication with it, which I hear was quite a difficult thing because they actually had to turn off all the heating on it in order to get the enough power into the transmitter and receive sites, or in the transmit site, to make the movement that they wanted to make. And they had to turn it off, and it takes 2 days to get there. Turn it off, make the maneuver, let it warm up, and it took so many hours to warm up, then give it the command to make the move, and then when it'd done that, to turn back the heating system back on. And you don't know the answer for 5 days.
90 years the power supply.
Yeah.
90 years.
Yeah. So
That's when the nuclear fuel.
That's right, yeah. So, just to give you an idea, this is what we're talking about. So here is the path loss. Here's a frequency, 14 gigahertz, right? So the math has all been nicely done for you. Okay. Lambda here is 0.2 of a meter. Satellite is, as we said, it's nearly 36,000 kilometers away. And if we do all the sums, we can see that the path loss is 206 dBs, 206 dBs. Now, I know I'm doing stuff at the moment up at 30 gigs, and I'm looking at path losses of, if I was doing it to a 36,000 kilometer satellite, it would be about 210, 211. I'm not. My satellite happens to be 414,000 miles away. And the path loss, again, it's not that much bigger. It's only 235. So it hasn't gone up by much, even though I'm going from 36,000 up to roughly 410,000. And if you want to know where 410,000 miles is, it's that big bright object that you see in the night sky. That's round and yellowy. Because that's where the project I'm working on, my next satellite's going. And it's a communication satellite, and it's going to be going round the moon. EIRP, 3 billion watts.
The same as the average Italian DX.
Yeah.
I'll remember.
Chris, could I just come in there? These figures are brilliant, you know, but the geostationary satellite is 36 kilometres
36.
directly above the equator.
Yes.
So the actual distance from the satellite to your...
Maybe even more than that, yes. Yeah, when we do all the sums... Oh, look! There's a satellite off to an angle. Right. So, the thing is, yes, as Don quite rightly says, all those nice numbers are great in terms of how far the satellite is away, if it's right above you. But, as we've already said, let's say Astra is at 29.2. So, it's at an angle, so you've now got to do a sum that basically says straight up is 36,000 plus this angle now over here, so it's now adding an extra, let's say 3,000 miles, so 3,000 kilometres. So this is now 39 kilometres, 1,000 kilometres, not 36. So, and that adds to all the problems, and then you calculate things from it. So, yes, we have problems of elevation angles. You also have other problems starting to come in, particularly if you're now using it at higher frequencies. You've got, as well as going through here, the atmosphere, if you were going straight up. The atmosphere, by the way, we take the atmosphere to be about 5 to 10 kilometres maximum. That's where weather finishes. Don't go on about whether it's finer ionospherics and things like that. We're only worried about, if you like, the weather. So the thick bit of the atmosphere, the stuff you can breathe. So we only go up to about basically the height of Mount Everest, if you like, and that's it. That's at the top of the atmosphere. However, as you said, if you start squirting off over there, if your satellite's down over there, it's a lot further away than it is if it was straight above us, and that must be taken into account. The other thing is that, when you're squirting out over here, you've got changes in polarization and everything else happening. So, 5 miles for the first is where the weather is. Now, this is, when we talk about the atmosphere, again, you're all down here. Even at 2 meters and 70 centimeters, down here. And so any absorption by the atmosphere is literally nothing, the square root of nothing almost. But as you go up in frequency, this absorption curves, as we call it, suddenly comes into play. One of the biggest problems is in this region here, between 20 and 30 gigs. And as you can see, there's a bump, the amount of absorption goes up and then drops back. And what we call the K band has one set of frequencies up at 30 gigs, but the down set of frequencies are at 20 gigs, so it lies either side of this hump. So it's less of a problem. Now, interestingly enough, if you go up to here, up to between 60 and 70 gigs, this thing shoots up here. Now, they do a lot of inter-satellite communications at this frequency. This is where all the intercommunications of the satellite come. Why? Because the satellites aren't affected by atmosphere up there in space. So this absorption doesn't exist between satellites. And if you shone it down into the Earth, of course, as soon as it hits the atmosphere, this thing comes into play and you can't see it. So therefore, it sort of makes sure that the whole thing is shielded for you. So the atmosphere acts as a shield for your inter-satellite communications. And there is more and more inter-satellite communications is happening. You go back not many years, and basically you had one satellite, there it was, you pointed your signals at it, and they went up and they came down. Nowadays, they want to be able to talk between satellites, particularly all these ones that are moving around. So it's more of a case of saying, it's like your mobile phone now with all the satellites that are up there. It wants to be able to hand off from one satellite to another satellite, but you don't realise that's what's happening. So you can talk to this satellite here, and you think you're going through this satellite here, and then that's moving there. But it's talking to this one here, and then when it says that signal's getting a bit low, it says, look, you take over, mate. And you just carry on. You don't know it's changed, and this one is going over, and so on and so forth. So intercommunication between satellites is becoming much more of a thing nowadays. And of course, the advantage of being up here at 60 to 80 gigs is everything is absolutely tiny. It's minute. Because if you think that at 60 gigahertz, the wavelength is 1 millimetre. 1 millimetre? No, half a millimetre. That sounds right. Half a millimetre. That's what the wavelength is. So you're talking... So even if you had an antenna, right, like we've had with the 13-metre dishes, this thing is now probably that sort of size with the same gain. It's probably no more than 5 millimetres across and has a gain of about 50. So this does have some advantages of working up between satellites up in that area. I won't go into that too much because even I'm not up to speed with what's going on. This is the big problem. Rain fade. Adverse weather. If we all lived out in the middle of the desert, it would be great because it would be nice blue sky and there wouldn't be a problem with rain fade. We don't. We live where it pisses down with rain every 10 minutes, except in Spain. Right. Your signal going through this cloud doesn't go very well. It can't see through the cloud. And it stops. As you probably notice occasionally when you've had incredibly big downpours of rain and suddenly the television picture completely disappears. And then maybe 5 minutes later, it all comes back on again. And that's all due to this problem. The thing is that, of course, it can happen at both ends. So it can happen at the transmitter end, where Sky are sending out their signals here, and or at your receive end. And you think, well, surely all Sky have got to do is just to turn the wick up. But as we've already said, you can't turn the wick up too much because of old F1, F2. So we have to be careful with that. And then we don't know when the rain's going to finish, and then suddenly you're blasting a signal into this satellite when the cloud's gone away. So, basically speaking, yes, you lose the signal for a short length of time. And we lost my thought. So, yeah, we lose the signal for a short length of time, and you just have to wait until it comes back, and that's it. But to give you some idea, C-band, which is down at sort of 3 gigs, the weather margin is about 2 to 3 dB. As soon as we get up to KU band, which is, as I say, that's your satellite TV signal, it's somewhere between 5 and 15. And at KA band, which is up at 20 to 30 gigs, it can be high as 50. So you're really losing a lot of signal. There is one other problem that you also get, which we don't have quite so much a problem as we do if you're more further south and you're not worried so much about the rain, you're worried about Mr. Sunshine. Because what happens there is that if your antenna is pointing up nicely in the sky and Mr. Sunshine comes across and goes behind your satellite, eclipses your satellite, there is more radiation coming out of Mr. Sunshine than out of your satellite. And so down the bottom where you're trying to receive your signal, suddenly it all goes to rats, the whole lot, boom, 20 minutes or more, while the sunshine just goes across like that. And that happens 2 or 3 times a year. So those are one of the other things. So rain fade is a big problem. But as we said, the main thing about this is that those are only sort of 4 or 5 miles high. They're not way up in, we don't worry about clouds that are up at 20,000 feet or something. They're minor things. Okay. Now, just before we started talking about this, I had a chat with Don, and I said, the thing is that there's a whole raft of other stuff associated with this lecture, which I'm not going to go into tonight. And that is to do with the digital signals that go up and down and how they work and all of that. And it's all down to this thing, carrier to noise thing. And Don said, yeah, if you like, I'll give a talk on where this one leaves off. And if you like, the digital part of it all carries on, because that's almost equally as important as the bits that I do. And that's what I've always said about the job that I do. As soon as it turned into digits, I hand it over to somebody else. So at this lecture, when I start getting into the world of the digits, I'll hand over to Don. And he said he's more than happy to give a brief outline of the way in which all the digits work. But what this is leading to is the receive side of everything. We've looked at the EIRP, and everything goes on about EIRP. And this is a thing that amateurs don't know anything about. And yet, in the world of the microwave man, this is absolute paramount. You need to know and understand this thing called G/T. It's called the goodness factor. And it is simply a measure of the antenna gain against the system noise. Now, when you're all doing your transmission, you go, oh, I've got a noise level and it's up at S9 or something like that. We're not talking about that. That's calls from locally. We're talking about noise that's created around it by space and things like that, which at microwave suddenly comes into play. At HF, VHF, the noise level is way down there. But as soon as you get up to a few gigs, the noise level comes up and up and up and up. And because we have to work out what that noise level is with respect to how our antenna is working, the antenna gain, we have this calculation that we do to measure this thing called G/T. So if you ever look at, if you go and look at a brochure for a satellite TV antenna. One of the things it should tell you is that's this figure there, because that's what you need to know. And if you're trying to compare one antenna system with another antenna for your satellite TV, that's the number that you want to know all about. The trouble is, you can fiddle it, and a lot of companies do fiddle it because it's important. It's one of those numbers that get fiddled, but I won't go into that. Right, so G over T is a measure of the antenna gain. So you've got the dish, there it is, gain 50. But then you've got to work out all of the noise. Now, where does the noise come from? Well, first of all, even if you put any antenna in, squirting out into space, it's going to pick up space noise. Now at HF, it's down there. As I said, if you go into microwaves, it starts to come up here. You can measure it. Now we measure this basically at 0 degrees centigrade, but we don't use centigrade here. We use degrees K, which is degrees Kelvin. So 0 degrees Kelvin is 273, right? Degrees K is 0 degrees centigrade, okay? Or the other way around, 0 degrees centigrade is minus 273. So 273 is the number that you have to realise. Then everything else creates noise. Your low noise amplifier, although it's low noise, still creates noise. And that has a number. You measure that, and that number is measured again. The amplifier measurement for the noise, it will give you a figure again in degrees K. And then you've got everything else, piece of coax, if you're using that in the system, that has noise in it. Everything you've got has got noise, because basically, how does RF travel? In a piece of coax, it's all the electrons whizzing along, right? And because it's all the electrons whizzing along, they're all colliding and they're all making noise. So everything, if you like, makes noise. And up at the microwave region, the noise gets bigger and bigger. So you can calculate the amount of noise for every single piece of component, add all the noise level up, and then what do? You do what you do everywhere. You do 10 log, that number, and it turns into dBs. So you've now got this one that's in dBs, and you've added up all the temperatures up here and turned it into dBs. And as I said, my job to do is to add up and take away sums, which is one lot of dBs from another lot of dBs. Okay, now bandwidth is also related to noise. And the thing about that is bandwidth is expensive. If you're trying to sell it, then if you only want to sell for 5 megahertz, it's cheap. But if you want to sell a few hundred megs, then it's more expensive. So, and more bandwidth requires higher EIRP. You need bigger amplifiers at more expensive, larger antennas. I mean, a 13-foot dish is probably going to knock you back about 2.5 million quid. And that's just for the dish, not all the other bits that go with it. That's just the dish, right? And then all of the other things you go with it, which we've talked about further on. Right, satellite tracking and pointing, right. Now, geostationary satellites, as we said, they're all nicely fixed in the sky, and it's quite easy to track them. But, so we don't have a bit of a problem with that. But even so, the bigger the antenna goes, the narrower your beam, the more you've got to try and track it, even though it may look as though the satellite itself is not moving, yet it is. As we've said, it's in this nice little box, which is about 140 kilometres. As soon as you get onto these ones that are whizzing around the Earth at only a few hundred kilometres up there, tracking becomes a lot more difficult. And even if you tried, as you know, if you've worked with the amateur satellites that are going over at this sort of height, about 250 kilometres, that your antenna is moving, you know, quite fast like this. So, which is why, again, if you look at all the modern news stuff about what's happening in the satellite field and picking up all of these microsatellites, etc., everybody is getting into the world of what's called electronically steered phased arrays. Now, a phased array, you know what a phased array is, I hope you might know what a phased array is. It's multiple antennas all linked up together to make a single beam. Now, about 3 or 4 years ago, I made a phased array, electronically steered phased array antenna, and for 30 gigs, 1,000 elements. And it was 6 inches square. So that gives you an idea of, you know, what we're dealing with here. So a lot of these phased arrays antenna, when they're working up in these very high frequencies, really aren't that big. You take 1,000 elements, and now they work with about 3,000 or 4,000 elements. So you've got tiles made up of these things. But the thing about them is that they've got everything incorporated within them. Within the electronics, you've got each element has got its own little transmitter power amplifier. It may only be 20 dBm, you know, barely sort of less than half a watt. But when you add up 1,000 of those half a watts, you suddenly find you've got a lot of watts. And if you've got 4,000 of them, you've got even more watts. Now, the thing about them electronically steered is the fact that if you add phase and amplitude to them, you can make the beam do this, or like that, or like that, or like that. And if you're really clever, you can create 2 beams out of it, which is always useful. So if you've got a satellite that's coming over like this, and you've got to track it, then if your antenna is electronically steered, it's dead easy to say, right, go over there, find the satellite, lock up on the beacon, and then just follow it through the sky, and it'll do it. And when it's lost it, you go and find the next one over here and follow that one. And you can't even tell that it's gone boom, boom, like that. It'll just do it. You know, I can't do it fast enough. Electronically, it can be done in microseconds. So satellite and antenna tracking now become very, very important with all of the modern satellites that are going up and all over the place. And really, I see it's 9 o'clock, so that wasn't quite too bad. I've skimmed the surface, very much so. There is so much more to it. As I say, and I haven't even got into the bit where we look at the actual signals themselves that we are sending out through space. I've just tried to basically look at the basics of the satellite itself and the ground stations and the way in which they work. So I hope you've enjoyed that. I see most of you are still awake and that you started to... Yes, Leslie. Start to understand how, you know, your sky signal gets to you and things like that. So if there's any questions, let us know. Yeah.
So that last one that you discussed, I guess that's how Starlink works, isn't it? Each tiny little bit.
Yes.
That's electronic rather than mechanical. That's electronic rather than mechanical, is it?
with all of these modern things, all the Starlinks and the OneWebs and all of that, because they basically are only visible for 20 minutes, 25 minutes at most. You know, some of them that are further out, you might get 40, 45 minutes out of them. You are really struggling to track them with old-fashioned mechanical methods. And they want these things to go on things that are moving as well in their own right. Yeah. So they want to put them on trains, they want to put them on boats, they want to put them on aeroplanes, and they're all moving. So if you like, the way in which the antenna is controlled becomes even more complex than just if it was a case of just watching it come over the sky and go back and over there. So you've now got a ship that's doing this while it's trying to watch this thing come over there, and it's rocking and rolling across the ocean like this, or you've got an aircraft that's going to do this, which, if you like, if you're on a passenger aircraft, an ordinary, they do things quite slowly, so that's not bad. But if you're in an F-35 and it does that, you need a system that can actually operate when your aircraft suddenly decides to do that. So,
Chris, I've got one for you. This is more to do with the sort of the low Earth orbit stuff. I'm very interested, as you know, in tracking weather satellites.
Yeah.
And the one thing I find, and I've never quite been able to puzzle out why, is I'm using a circularly polarised antenna, quadrifilar helix, and if I've got a satellite pass which is going almost directly overhead, the pictures I get are usually pretty awful. Whereas if it's off...
That's because of the radiation pattern of you're not looking at the radiation pattern of your antenna.
Right.
You've got a circularly polarised antenna.
Correct.
Which is doing that.
Yeah.
Right?
But it's mounted.
There ain't any, there's nothing here.
Yeah. It's vertically mounted.
Doesn't matter.
So what you're saying is what's coming...
There's nothing here.
Yeah, so it has no gain in the vertical direction.
Right. Basically, imagine it like a creamy donut.
Yep.
Right. Your radiation pattern looks like a donut. A Krispy Kreme donut, ring donut, like that. So if you had that, if you imagine sticking your antenna with the donut on it, and the donut is the if you like, what's being radiated. You've got loads of signal out here of your donut, and then it slackens off until eventually in the middle you've got a bloody great big hole.
So really, anything then up to, for example, maximum elevation of about 60, 70 degrees.
Roughly, first of all, right. One thing to remember, all right, although you won't probably do that. Is that, yes, your donut, it's basically, if you like, it's like a monopole, a vertical monopole. Imagine it's just like a vertical monopole, right? And if you took your vertical monopole on the ground plane like that, and I transmit it to you with a similar monopole, we have good conversation. Now, I'm going to take my monopole like that on a ground plane, and I'm going to do that. So that my monopole is now doing that to you, and you won't be able to hear me. Because you're going all the way down into that hole and all the way out the other side. Your antenna is doing exactly the same thing. It's all nicely circularly polarised here, but as it comes up here, you will start to lose it, and you're going down into the hole down in the middle. There is no energy down through that plane.
So basically then, when I'm looking for satellites to actually try and download the images from, the higher the elevation is not...
It should work best from somewhere between 10 to 15 degrees above the horizon, up to about 60. And then after that, you get what you get.
That seems to be that's kind of what I've experienced.
One of the other things is that you will also lose part of your circular polarization. Because whereas you have got two phased antennas, right, down at these angles, once you start getting up here, as I just said with you, with your monopole, so imagine you've got that monopole, so there it is, and I do that, it's disappeared.
Makes sense now.
So you've only got linear polarization coming up here, and it's the wrong one.
How do you compensate for that?
How do you compensate for it? Well, you basically have another antenna that basically is, if you like, is a helical like that. Now, if you take a helical on a ground plane like that, probably about 3 turns, it's going to have a beam shape exactly like that. Okay? So there's no energy down here between 0 and about 25, 30. So where Jeff picks up all of his best signals, this helical is not. It's not going to pick up anything down there. Whereas when it goes over the top, it's got all his gain and signal is all the way up there. You've now got gain up there of 4, 5, maybe 6, 7 dBs.
I'd like to speak to you more about this because the antenna I'm using is actually the quadrifilar helix.
Yeah, but just because it's a quadrifilar helix doesn't mean to say it produces if you like, a circular radiation pattern.
Understood. Okay.
It's not going to do that.
You need a quadrifilar going upwards.
Yeah.
Because your signal's coming down like that. Because it's spinning as the
And just, yeah,
so
you
you need, to get it in the beam.
and you have to remember that
Because the
you
QFA
lose,
radiation.
you don't get CP throughout the full 90 degrees. So you're going to lose it. You're going to lose the vertical component.
Okay. I won't hold the rest of the cover. Any other questions?
Anybody else? Go on.
Yeah, I used to get on the Woolwich ferry. It seems a strange thing, but when I was in London, you'd often get a call to go south of the river, quickest way,
Yeah.
on the Woolwich ferry. As you went round the corner at the Woolwich ferry, there used to be a bloody great earth station. Do you know if it's still there and if it actually produces
No,
sky
because
or-
I think
Would probably be what was marketed in the 70s and 80s as the Intelsat business.
yeah. It's, I was going to say it's just one of the
Well, it had
professional.
more dishes than I've had.
Yeah. It's one of those.
Bloody enormous.
Could be Intelsat, Inmarsat, or one of those.
Yeah.
Or even the early, maybe the early Sky days would have had theirs there.
Yeah.
Maybe.
Yeah.
There, and if you take
The opposite Euston Station used to be the Inmarsat headquarters. They used to have dishes on top.
Yeah.
Yeah. But you couldn't see them from the ground. They were 20 odd stories.
Feet out there.
Yeah.
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 And then, but most of them probably would only be 6 to 9 metre antennas. They probably,
Yeah, they look quite large.
if
when
they're
you're
up
driving
high,
around
they
in the
won't
car.
be much bigger than that.
Yeah. Give an example what Chris was talking about going. We had, where I worked down at View, we had 105 foot dishes, 90 metre dishes,
Yeah.
a forward gain of 90 dB. So we were pointing at the satellite over the Indian Ocean. So goodness knows what our slant.
54 degrees east
Yeah.
it is.
53 degrees east was our. We used to go 70 east to 70 west,
Yeah.
but we were going right the way through the atmosphere. So when the sun, we used to get the sun down there.
Oh, yeah. Yeah.
And don't get the wrong impression that when you see the satellite dishes, and some of them have these sort of football-looking radomes over the top,
Yeah.
that they're secret. They're not. Some of them are, some of them are not. What you have to remember is that if you've got, like Don says, a dish that's 100 foot across, 80 feet across, the concrete pad that has to sit on is huge and very heavy, because basically a very strong wind, even for a 13-foot dish with the pad the wrong size, can just blow it over.
Yeah.
Now, one ways to stop that is to basically put it in a radome, and then the wind can't blow that over, and wind will behave differently over a curved surface than it will against a dish, which basically, you know, if it's pointing in the wrong direction, it really amplifies the wind as much as it amplifies all your radio signals. So
there's a lovely story about that. I'll just throw one in here. We had a dish built in 87, 88, and it was going to go inside a radome. The radome is made of canvas, and it was sealed at the bottom and inflated. And when it went on, it was just a big bag, and it was brown in colour. The idea being that after about 6 months in the sun, it turns white, but it's been treated with this chemical. So in November, just before Christmas, they draped this great brown bag over this 90-foot dish. We blew it up and then put an aircraft warning light on front. So some wag in the local feud paper drew this with a holly leaf on the front. It looked like a giant Christmas pudding. You know, it was you could see it from miles away. It was like this giant Christmas pudding. It looked like a bit of holly on the top, you know. I mean, 6 months later, it was just another white dome, you know. But
those
sketched this and put it in the local feud paper, you know. Wonderful. Walthamstow now has the biggest Christmas pudding in the world.
Those inflatable radomes are made by a French company called Saint-Gobain. That's who makes those.
Any more questions for Chris?
Any more?
I just throw in one more bit about talking about steerable antennas.
Yeah.
When the Russian Navy started using the Molniya satellites, dear old GCHQ didn't have anything to track it. So they built a dish. The only thing they could find that had the speed to go from, as that satellite was disappearing, to get back round under 80 degrees, an old Royal Navy anti-aircraft gun mounted, and it literally, an old World War II ACAT gun mounted, and it could spin round. And this thing used to...
Good thinking, boys. Somebody there.
Yeah, you know, this was sort of late 60s, early 70s, you know.
Fantastic.
There we go.
Right,
Okay.
in which case then, gentlemen, can I ask that we just thank Chris and the...
Thank you.